What's the name of that? So how many carbons are in the longest chain? Hmm? I think 7, right? 1, 2, 3, 4, 5, 6, 7. I think it's 7, right? Right there should be 7. So that'll be heptadiene. Oh, I'm going to pretend that I have enough space for numbers in there. And what are the other substituents? Methyls. How many? Lower. 2. So this one right here is part of the longest chain, right? So you don't count it. So it's 2. So you've got dimethyl. So do I number it red direction or do I number it green direction? Green, because alcohol is most important. You want to make sure it has the lowest possible number. So this is going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be 1-all 3,5-diene 2,4-dimethyl. What else do I have to do? E or Z? Yes. Hopefully that'll go away in a second. So now I've got to do 3, 5, E or Z. So let's look at the double bond at 3. We break it in half. This carbon, we're comparing a carbon versus a hydrogen, right? So the carbon chain has higher priority. On this carbon, we're comparing carbon and carbon were tied. Compare hydrogen and carbon, carbon wins. So the two high priority groups are on opposite sides. So that's going to be E. Remember something, so good. Or at least from Monday you remember something. All right, and then double bond 5, break it in half, we'll make it green here. Right, the red side, hydrogen versus carbon, carbon wins. Blue side, hydrogen versus carbon, carbon wins again. The two high priority groups are on the same side, so that's Z. So 3E5Z, 2,4-dimethyl hepta 3,5-diene 1-O. There you go. Super easy. So now we're going to start doing some reactions. I'm going to start doing reactions of dienes. And there are two types of dienes that we're going to be concerned with the reactions of. First is going to be isolated dienes. And for isolated dienes, the double bonds react like they're different molecules, right? They're too far apart to talk to each other or interact. So the fact that there's another double bond in the molecule doesn't impact how this double bond is going to react, right? So each double bond reacts independently of any other double bonds in the molecule. All right, so if I have one equivalent of HBr, right? So I have two pi bonds in my molecule, and 1 equivalent of HBr, that means I only have enough HBr to react with one of those 2 pi bonds, right? So can make my product. It doesn't matter here which double bond I react with because the molecule is symmetrical, right? So it's just going to react with one side or the other. Doesn't matter. Just going to make the same product regardless. Everyone on board? Now the difficulty lies in when the double bonds aren't the same, right? So let's say we have our 1 equivalent of HBr. And now we have to know which one of these double bonds I'm going to react with. I can only react with one because I only have enough HBr to react with one, but I need to know which one, right? So the general rule of thumb is the most substituted double bond reacts first. So you're going to pick the double bond that has the most groups on it, and that is going to be the double bond that reacts first. So double bond A here has 1 group on it, right? It has just that 1 carbon chain. Double bond B has 2 carbons on it. So double bond B is going to react first. And the question, I guess, then becomes why? Why is this the case? Why the more substituted double bond reacts? And there's 2 reasons. First, oftentimes the more substituted double bond makes a more stable carbocation. Right, so if you remember the mechanism, never forget, right? If you remember the mechanism for this, right? I'll draw it out real quick. But I'm going to compare, I need to go to another slide, but I'm going to compare A and B, right, with the carbocation they generate. Right, so if I take double bond, if I take this, and I react with double bond A, right, I'll make that carbocation. If I react with double bond B, I make that carbocation. What kind of carbocation is that? Is it primary? Is it secondary? Is it tertiary? It is secondary, right? It's bonded to directly bonded to 2 other carbons. It's secondary. What kind of carbocation is that? Tertiary. Right? Which one's more stable? Tertiary. Okay, just to refresh everyone. Right. Tertiary is more stable than secondary, which is way more stable than primary, which is way more stable than methyl. General rule of thumb is we're allowed to make secondary and tertiary carbocations. We're not allowed to make primary methyl carbocations because they're not stable enough. So the first thing you can think about is that having more groups on your double bond was going to lead to a more stable carbocation. So that's one reason you can think that, okay, the more substituted double bond is going to react first. Reason number two is that carbons are electron donating, and more carbons, or I should say so, more carbons makes the pi bond, the double bond, more negative. All right, so carbons donate electrons to other carbons. They give electrons to other carbons. So the more carbons you have on a double bond, the more things you have pumping electrons into that double bond. So a disubstituted double bond has two carbons giving that pi bond electrons. So that pi bond becomes a little bit more negative and is a little bit more likely to go add to something that is positive because it has these carbons giving it electrons. Where if you have a monosubstituted double bond, you only have one carbon giving that double bond electrons. So it's a little bit less negative, thus less willing to go add to something that is positive. So the more carbons you bond to your double bond, the more electron density that double bond has, and the easier it is for it to go out and add to something. That make sense? So those are the two things. You get more stable carbocations a lot of times, and the double bond is just a little bit more negative the more groups you have on it. So which double bond do I react with? Do I react with A or do I react with B? A. A has three groups coming off of it. B only has one. A is the more substituted double bond. What do I add to said double bond if I'm adding Cl2? You add a chlorine to each carbon. Those chlorines, do they end up on the same side or they end up on opposite sides? Opposite sides. Yep. Right now, we don't know which chlorine's up and which chlorine's back. So if you flipped it around and made your top chlorine a wedge and your bottom chlorine a dash, which is what I did in the first class, that's perfectly fine. That's 100% right. Right? As long as they're on opposite sides. Which double bond am I going to react with here? B. Right? It has three groups on it. A only has two. All right, now you decided which double bond you're reacting with. Now you have to decide, are you going to put the chlorine on carbon 1? Or are you going to put the chlorine on carbon 2? Carbon 1, because carbon 1 will make a tertiary carbocation, while carbon 2 makes a secondary. Reasonable? Which double bond am I reacting with? B. Right? B has 3 things on it. A has 2. Right? Because you're just counting, right? There's no carbons on this side. 1, 2. For B, there's 1 carbon here, 2, 3. And all you're doing is you're just counting how many groups are on there. Now that you've decided that it's adding to B, do you add to carbon 1 or carbon 2? Carbon 1. Again, it's the more substituted of the 2 carbons, so the bromine goes there. It's really bad. A. Which am I adding? Which double bond am I adding to? A again, or A this time, and then 1 or 2? 1. Well, I guess it doesn't really matter here, right? Because I'm adding Br2. But yeah, if it was HBr, it would be 1. So, because I'm adding a bromine on each side. Here, I don't have to worry about stereochemistry because I'm only making 1 chiral center. So I don't have relative stereochemistry.
I was asked to explain why there's no stereochemistry in these 2 bromines.
This carbon right here isn't chiral, right? It's got 2 methyl groups on it, the bromine and then the longer chain. So that carbon isn't chiral. And so what you're showing with the wedges and dashes when you add like Br2 or Cl2 is the relative stereochemistry that the bromines are on opposite sides or the same side, right? And you can only have opposite side and same side if both of those carbons that you generate are both chiral carbons. So this carbon right here, this carbon is chiral, right? It's bonded to 4 different things. The black carbon isn't chiral, so I don't have to worry about wedges and dashes because I didn't make 2 chiral carbons. That makes sense? Awesome. Now, if I have 2 equivalents of HBr in this case, I have enough HBr to react with both of my pi bonds, right? So I'm going to get rid of both pi bonds here. But because, nothing's ever easy. So I can add my bromine to one side. That's cool. That feels right. Now this other side's trickier. Think about the mechanism. What do you always have to do if you make a secondary carbocation? You have to see if it can rearrange. Right, so this is a secondary carbocation. I can move a methyl group. Now my Br minus will add to that. Yoink. Eat your product. So remember, whenever you have a secondary carbocation, you need to look and say, can I move a methyl group? Can I move a hydride? Or can I do a ring expansion to make a more stable carbocation? So this guy right here is our product. So like, other than throwing in a rearrangement to, without any kind of trigger warning, just like boom, just like setting you back into like the worst times of your life, right? Everything seemed good. Isolated double bonds, you're just gonna figure out which double bond has the most groups on it, and that's one that's gonna react first. And once you determine that, then you just treat it like a double bond in a molecule with no double bond, and you just follow all the rules you would have done in organic one. for alkene reactions. Now, the other type of double diene that we need to worry about are conjugated dienes. So these are close enough that they have resonance, that they interact before a reaction starts. They are going to interact during a reaction as well. This leads to two possible products. Right, so we have our diene, or one equivalent of HBr. We can get two products. The first product is the product that you kind of expect, right? Where you add the hydrogen to one side, bromine to the other, and you get your bromide. The other product you can get is that where the hydrogen and the bromine are further apart. This first product is called the 1,2 product because the hydrogen and the bromine are 1, 2 carbons apart, right? There's 2 carbons between the hydrogen and the bromine. The other product is the 1,4 product. 1, 2, 3, 4. Here there are 4 carbons between the hydrogen and the bromine. So we get these products from kind of the same mechanism. So let's look and see where these come from. Right, so the beginning is the same, right? The pi bond is going to add to the hydrogen, break the hydrogen-bromine bond, and make a carbocation. So you're always going to make the allylic carbocation, so the carbocation that is beside the double bond. Right, and I guess here's my hydrogen to be 100% nice. There you go. Right, so if you get this carbocation and you immediately add your bromine to it, you get the 1,2 product. The 1,4 product is the result of resonance. So you've got a charge beside a double bond, so you're able to move that charge. So I'm going to redraw the carbocation we have up here, just so there's space. These electrons can come over. I can make that carbocation. Now if I add my bromine to that carbocation, I get the 1,4 product.
So I just got asked how and why you would select for the 1,2 versus the 1,4 product in a reaction.
One is the reason you'd want the 1,2 versus 1,4 is like if you're trying to make something and you need the 1,4 product, right, versus the 1,2, you need to be able to select for that, right? And so we're going to go over how you change the reaction conditions to favor making the 1,2 product versus favor making the 1,4 product. So there's a reason to make one over the other, and there's a way you can pick. And we're going to talk about how you pick here in a second. So you've got your carbocation here, resonance happens and it moves it. Now you might just be thinking, wait a minute, he said like 3 slides ago that we aren't allowed to make a primary carbocation, right? And he's drawn a primary carbocation. This carbocation, right, is primary, but it's also allylic, right? It's beside a double bond. So it's more stable than just a bare um, carbocation that's primary. So it has closer stability because of that double bond to being like a secondary carbocation. So we're allowed to make that one, but I couldn't just make just a primary carbocation. That's a no bueno. We can't do that. But if you had the double bond there, then you're allowed to. So I'm not lying to you. So it's fine. So when I say always make the allylic cation, right? So here, the allylic carbocation also is the most substituted carbocation. But what if you have a situation like this, right? That either carbocation that you make is going to be secondary, right? So if I add to this, that's a secondary carbocation, or I could add in such a way that it's secondary but also allylic, right? I could add that hydrogen to either side of that double bond. This is going to be more stable because, again, it has that allylic, it has that double bond to give it resonance. So you're always going to favor making the allylic carbocation because it gives you resonance in your stability. So right here, our two products would be 1,2 plus 1,4.
I was asked to explain why resonance leads to more stable carbocations.
Because of resonance, right? So this carbocation has a resonance structure where I get to move that charge to another carbon. So instead of up here in black, that carbocation is always stuck on that carbon. That carbon is 100% positive. In the green version, right, this carbon right here is sharing its positive charge with that carbon there, right? So that charge gets spread out. So there's not one single carbon that is 100% positive. So it's just easier to do, right? It kind of goes back to the couch analogy, right? The black carbon has to carry the couch all by himself. The green structure is spreading that weight out across multiple friends. So it just makes it easier. Which double bond reacts first? A. Same rules as when they're isolated. Whichever one has the most substituents on it is going to be the one that reacts first. So that's going to react first. We're going to want to make the allylic carbocation. So even though we're making a secondary carbocation as opposed to a tertiary, because it's allylic, we get to do that, right? Because the resonance gives us that much stability. And then I can make my two products, right? I can have my 1,2 product plus I can have my resonance structure where I move these electrons over. I can have my, oops, wrong spot, 1,4 product. So always err on the side of making the allylic carbocation. So let's say we have one equivalent of Br2, right? So again, we got to decide which double bond we react with first. Boop. A or B? B. Cool. And we're going to get our two products. Oops. And again, since I'm not making two chiral centers for the 1,2 product, I don't need to worry about stereochemistry. And I never have you worry about stereochemistry in the 1,4 product, and I'll show you why here in a sec. Do you guys remember the mechanism for this? You do. You just don't want to. You want to make me feel useful. I understand. I appreciate that. Right. So you make your rhomonium ion, right, and then your halide can add to it, usually the most substituted side, and that'll make your 1,2 product, right? But we can take that same rhomonium ion and use the double bond and a little bit of resonance action here and pop open the bromonium ion. And now make a carbocation that is now far away from the bromine, and then add our other Br minus to that. So even though this mechanism doesn't go initially through a carbocation, you can still use resonance to make a 1,4 product, even though you're going through like a bromonium ion or a chloronium ion. So now we're going to talk about selecting 1,2 or the 1,2 or 1,4 product. So how do we pick one or the other? Right? This is mainly accomplished by temperature. All right. And so reactions that are controlled by temperature are usually said to be under the control of one of two things. So there's kinetic control, and there is thermodynamic control. When a reaction is under kinetic control, the product that forms fastest is major. So under kinetic control, it's just a race. Whichever compound is made more quickly is the one you get the most of. Thermodynamic control is the more stable product. Oops. The more stable product is major. Right? So whichever product is lowest in energy is the product that you get the most of. So reactions under kinetic control, right? For me, I keep it simple. The temperature is going to be 0 degrees C and below. The temp for thermodynamic control is going to be roughly room temperature, which is about 20 degrees C, roughly, and above. Right? So under kinetic control, You get one shot at your product ratio, right? You do the reaction happens one time, and however much of the kinetic product you get, that's how much kinetic product you get. If your ratio is 95% kinetic product, 5 thermodynamic product, it's not ever going to change, right? You get one try at it and you're done. Thermodynamic reactions are under equilibrium. So those reactions go back and forth. They're going to make both products, and then the less stable product is going to go back to the intermediate and try again. And eventually it funnels all of it off to the thermodynamic product. So the kinetic control, it's one and done. You get one shot and then it's over. Thermodynamic control, the reaction just tries over and over and over and over and over again until it funnels everything to be the most stable product it can be. Right. So why does all this work? We're going to revisit what I'm assuming is like one of your favorite things from Organic 1. You know where I'm going? Reaction coordinate diagrams. Woo! Right, so remember reaction coordinate diagrams. The y-axis is energy. The x-axis is reaction progress, right? So if we just have a generic, simple diene reacting with like HBr, we get our two possible products. Right? We can use a reaction coordinate diagram to kind of explain why we're getting, why we have these reactions under thermo and kinetic control. So for us, the 1,2 product is always going to be the kinetic product, right? We're going to just assume that's going to form faster. In the 1,4 product is going to be our thermodynamic product. We're going to assume that that product is always more stable. Right? So if we look at our reaction coordinate diagram, we have our starting materials over here. They come up, they go to some intermediate, and then that reacts to give two possible products, right? We're going to have our kinetic product, right? And we're going to have our thermodynamic product. Right? So our intermediate that both of our products share is going to be our allylic carbocation, right? The path to the kinetic product, the black path, has a lower activation energy, right? Right? It is easier to go from the intermediate and get over that activation barrier than it is to get over the green one, right? Because the green one's much higher. So our transition state on the black path involves our Br minus making a bond to a secondary carbocation, right? Versus the green path involves our bromine making a bond to a primary carbocation, right? Primary carbocations, even though it's allylic, are going to be less stable than secondary carbocations, right? So that helps explain the difference in energy, is that I have a more stable carbocation when I'm making the 1,2 product than I do when I'm making the 1,4 product. Fair? So when I run the reaction under kinetic conditions, under low temperature, I'm only giving the reaction enough energy that the molecules go over the black path, right? They get to the intermediate, There's not a lot of energy in the system, so they just go over the easiest to get over barrier, and they make the kinetic product, right? I'm not giving them a bunch of energy because it's cold, so they just go over the easiest barrier, right? Under thermodynamic conditions, I'm giving them a bunch more energy, right? It's much warmer. So when they get to the intermediate, they're able to go over both the green path and the black path, and they'll make both products. But under thermodynamic conditions, the less stable product is able to go back to the intermediate and try again. So maybe the first time you run the reaction, maybe you get 99 kinetic products and one of your thermodynamic product that you want. Well, then all that 99 kinetic goes back to the intermediate and tries again. And now maybe you get 98 and 2. And that just goes back and forth and back and forth and eventually funnels everything off to the more stable compound. Right? So at low temp, you get one try and you go over the easy to get over barrier. That's kinetic control, thermodynamic control. You have enough energy that you can go over the higher energy barrier to get to the more stable product. But you have to keep doing it over and over and over again because you're always making both until eventually you funnel it all off. Make sense? Seem reasonable? So why did I get to say that the 1,4 product is always thermodynamic, always more stable, and the 1,2 product is going to be kinetic and probably less stable? So let's look at these two products here and compare them. Oops. All right, first let's compare our double bonds. So in the 1,2 product, the double bond that we make or that we have is mono-substituted. And in the 1,4 product, it's di-substituted. Di-substituted double bonds are more stable than mono-substituted double bonds. So this is more stable. More stable double bond. All right. Now 2, let's look at the bromines. All right. Bromine's a big element, right? So this secondary bromine, it's banging into the other carbons that are near it. And there's a steric interaction there, right? This bromine is banging into this carbon, banging into this group here. So there's sterics that are destabilizing the molecule, right? Because you've got this big bromine and it's smashing into stuff. When you have the 1,4 product, that bromine is sticking out into space, right? It gets a point away from everything and it's not hitting as many groups, right? It can arrange itself so it doesn't bang into stuff. So there's less steric interaction here. Right? So the combination of having a more stable double bond and being able to put your halogen or whatever group you added away from the rest of your molecule and reducing sterics leads to the 1,4 product being more stable. Now, this is like for a really simple example. It's harder to predict if you have more groups on your molecule or your double bonds. You know, like your diene isn't like just one 3-butadiene, right? But we're just going to assume for like your sanity, right, that the 1,2 product is always going to be the more stable product and always going to result from kinetic control. So always from kinetic control, right, 0 degrees and below. And 1,4, so 1,2, 1,4 will be always thermodynamic. Letters are hard. All right, so we're always just going to assume that. So even when things get a little more complicated, it might be harder to see, we're just going to fall back on that, make our lives easier. So on Friday, we'll do a bunch of examples where I give you different temperatures and make you tell me if it's 1.2 or 1.4 product. And then we will move on from there to Diaz-Alder reactions, get height. So I will see you guys on Friday.